Okay, so in this video we are going to study or apply all the concepts that we've developed for dynamic fluids into problems. Okay, the three main things that you really need to keep in mind is the equation of continuity, which says that A1 times V1 equals A2 times V2. Here A is the area, V is the speed with which the fluid is flowing. The definition also of the volume flow rate is something important, and volume flow rate is volume over time, and it is equal to A times V. Now the lowercase v here once again is the speed, so make sure that you keep that in mind. And then last one is Bernoulli's equation, which says that the pressure plus the pressure, which happens to be work per unit volume, plus kinetic energy per unit volume, plus potential energy per unit volume, is equal to constant, okay, for the ideal fluid that we are going to look at. Okay, so let's apply this first to a simple problem, and this is what happens. This is the problem. Let's say that you have a pipe where we're looking at some portion of the pipe, and the cross section say changes in this manner. So let's say the radius on this side, R1, is equal to say 5 centimeters, and the radius out here, let's say, is equal to 2.5 centimeters. And let us say that you've been told that the fluid flows in this to the left hand side with a speed of say 3 meters per second, and the pressure on the left hand side is equal to, let's say, it is equal to 1.2 atmosphere. Okay, and the question is, what is the pressure on the other side? Okay, now to find the pressure, what we need is what we need to do is use Bernoulli's equation. But if you look at Bernoulli's equation, what we need here is, we have the pressure on the left, we have the velocity, we have the height. Okay, the height is not changing, so we'll take that to be 0. On the right hand side, the P2 is what we are trying to find. V2 is one of the things that we do not know, but we need to find V2. Okay, so in order to find V2, first we're going to use equation of continuity, which says that A1 V1 equals A2 V2. Now let's write down the area on the left hand side. It is equal to pi times 0.05 square times V1, which happens to be 3 meters per second, and on the right hand side it is equal to pi times 0.025 square times V2, where V2 is the speed on the right hand side. Okay, now do not plug all these things into the calculator at this point. Just wait, and you see that a lot of things cancel out. First of all, we can get rid of the pi's cancel out, and then what we'll do is we'll write V2, okay, as 0.05 square times 3 divided by 0.025 square. Now 0.05 divided by 0.025 is 2, and the square of that is 4, so 4 times 3 is equal to 12 meters per second. So you see, you could do this without using a calculator. Alright, now that we have this, we'll use Bernoulli's equation. Okay, and what that allows us to do, okay, is very simple. The pressure at one point plus the 1/2 rho V1 square plus rho GH1, okay, is equal to the pressure on the other side plus 1/2 rho V2 square plus rho GH2. Great. Now that we have all our terms, let's plug it in. First of all, the pressure on the one side is 1.2 atmosphere, so this is 1.2 times 1.01 times 10 to the 5 plus 1/2 times, let's say it's all water, so it's 1000 times V1 squared, and the V on the left hand side is 3 plus 0 for this term plus P2 plus 1/2 1000 times 12 square plus 0 again for this, because the height is the same, so we don't have to worry about it. Okay, so now in order to do this, all we need to do is solve for P2. If you do it correctly, you'll end up getting 53700 Pascal. Okay, so that's one application of Bernoulli's equation. We'll look at a few more.